Hello and welcome, stat students, to the final video for the final section of the final chapter of our book. We made it. Here we go. We're going to finish up transforming to achieve linearity today. So, we're going to revisit power models today. So, a couple days ago we looked at one way to deal with power models. We're going to look at another way today that uses logarithms. So, basically, here's what we do. Here's, I guess, the reasoning behind what we do. So if the power model has this form, and A and P are constants, then what you can do is you can take the logarithm of each side and you get this. Now, using the rules of logarithms, you can separate this out into log of A plus log of x to the power of P, and then using another rule of logarithms, you can bring that P down in front. All right, and now what you can see here, log of A is a constant, P is also a constant, so you can imagine this is like the y-intercept and this is like the slope, and then you've got log of y equals log of A plus P times log of x. So this equation right here shows that taking the logarithm of both x and y results in a linear relationship between log of x and log of y. And if you look carefully at this, you can see that P, the power of the power model, actually becomes the slope of the line that links log of y to log of x. So the idea here is that if a power model describes the relationship between two variables, a scatter plot of the logarithms of both variables should produce a linear pattern. And then you can fit the least squares regression line to this transform data and use a linear model to make predictions. And the nice thing about this method is you don't have to know what the power is going to be ahead of time like we had to in the other method. We had to know whether it was going to be a squared or a cubed. And then use that number. Using this method, you don't have to know that ahead of time. So, let's take a look at an example. On July 31st, 2005, a team of astronomers announced that they have discovered what appeared to be a new planet. It was originally named UB313. The potential planet is bigger than Pluto, and it has an average distance of about 7.5 billion miles from the Sun. So could this new astronomical body, now called Eris, be a new planet? Now, at the time of the discovery, there were 9 planets in our solar system, and here is the data on their distance from the Sun in astronomical units, or AUs, and the period of revolution of those planets in years. So, what I did here, and what I'd suggest you do here, is go ahead and type this data into list 1 and list 2. So list 1 is distance from Sun, list 2 is period of revolution. And then if you look at a scatter plot here, you can see a slightly curved relationship. Now, it might look like a line would fit that pretty well, but you would notice that the points on the end would be above and the points in the middle would be below, which would give this pattern. And really, a slightly curved line would better fit this data. But what I'd like you to do first, describe the relationship between these two variables. Now, I hope you remember that when you're reading a scatter plot and you're asked to describe the relationship between two variables, you want to talk about form, direction, and strength. Those are the 3 words we use for scatter plots: form, direction, strength. So form is talking about the shape, so we would call this a nonlinear shape. Direction is positive. As one variable gets bigger, so does the other. And strength, how strong of a relationship is this? So I would say it's very strong, positive and curved or nonlinear relationship between distance from Sun in astronomical units and period of revolution in years. Next thing we're going to do, based on those scatter plots, explain why a power model would provide a more appropriate description of the relationship than an exponential model. So basically, here's what we're going to do. We are going to take these two variables and transform them. And we can make these graphs on our calculator by doing the following. I'm going to go Stat, Edit, and I'm going to go to List 3. And what I'm going to do here is I'm going to press up, and I'm going to hit ln of List 1. Okay, so now it's going to take list 1 and it's going to do the natural log of each of these numbers and put it in list 3. Then I'm going to go over to list 4. I'm going to press up and I'm going to hit ln of list 2. So basically this list 4, will be the natural logarithm of list 2. And now what I'm going to do is I'm going to see if this graph, so I'm going to plot the distance compared to the ln of period of revolution by going to my scatter plot menu. And now I want to leave the x variable alone, which I had in list 1, but now I want to plot it against the natural logarithm of my y variable, which I put into list 4. And then I'll hit zoom 9 to change my window to make it fit. And you can see this very curved relationship, which means this is not a linear relationship between, my x variable and the ln of y. All right. But then what I'm going to do is I'm then going to go back to my scatter plot. And instead of plotting x compared to the ln of y, I'm going to compare ln of x, which I put in as list 3. So now I'm going to do list 3 compared to list 4. And then again, I'm going to go zoom 9 to change my window. And you can see this relationship here, this graph is very linear. And this is ln of x compared to ln of y. So that's how you can make these easily on your calculator. And this will tell you whether a power model or an exponential model is appropriate. Because this graph was curved, that means an exponential model is not appropriate. Because this graph right here is fairly linear, that tells us that there is a strong linear pattern in this relationship between these two variables, the ln of x and the ln of y. So that means a power model would be appropriate. So that's what you can look for. Then you can run a linear regression or have a computer run a linear regression of this data here. And we could do that on our calculator by going to Stat, Calc, and now I'm going to go linear regression, which is option 4. But I want to do a linear regression of these two variables. So on my x-axis is going to go the ln of x, which is list 3, and on my y-axis is going to go the ln of the y variable, which is list 4. And then, sure, I'll store this in y1 and calculate. And now you can see, the slope is right here, about 1.5 or 1.49. There's the y-intercept. There's r squared and r, so you can see those same values from this output table. So to write the equation, I'm going to use this slope and this y-intercept. So there's the y-intercept plus the slope, but remember that instead of x, it's ln of x. So it's the ln of distance I plug in there, and then the ln of the period that I plug in there. And it's, hat because it's a predicted value for the ln of period. All right, so there's my equation that I get. Next, let's predict the period of revolution for Eris, which is about 102.15 astronomical units from the sun. So what I can do is I can plug in 102.15 into this equation right here for distance, because that's how far away it is. So I can use my calculator to evaluate that. I get 6.939, which is the ln hat of period equals 6.939. So that's not my final answer. I need to then, solve this for period by doing, let's see, I can go second ln to get e to the power of 6.939. And so there's my prediction right there. The predicted period is about 1,032 years. All right. And then just an FYI, a nice shortcut on your calculator here is, since I stored this equation in my Y menu already, I could do this right here and do y1 of 102.15. But let's move on to part D. Let's take a look at a residual plot. All right. which on my calculator, I could also do that because the last thing I did was run a linear regression. The last linear regression I ran was of list 3 and list 4. So it stored all the residuals in its memory. So I'm going to go to my stat plot, and I'm going to make this residual plot on my calculator by putting the ln of x on the x-axis. So that would still be list 3. But then on list 4, I'm going to do stat, I'm going to go second stat and go down to the bottom of that, and I get residuals. That's where I find the residuals. And then I can hit zoom 9, and then it changes the window, and there are my residuals right there. So that's how I can get the residual plot on my calculator. Now you'll notice that there is a clear pattern in this residual plot, which maybe would have led us to believe that a linear model was actually not appropriate for this data. But when you look at this data, I mean, it's clearly very linear. So what's going on here? Well, when you look at the sizes of the residuals, they are very small. So this is this linear model actually does a really good job. It's just, you know, when you're in this area, you're going to get probably a positive residual. Here in this area, you get a negative residual, and here you get a positive residual again. So what we think is going to happen is if we plug in this number, where would that fall, you know, compared to these points? So if you plug in, and actually I'm going to do the ln of 102.15, I get about 4.6. So on this graph, 4.6 would be like right out here somewhere. So like, where is this residual going to fall? Well, if this pattern continues, my guess is that the residual be somewhere in here, which you can see is above the line 0. Now, what does that mean if the residual is positive? Well, since the formula, so this point would fall to the right, which would have a positive residual. And since the formula for residual is actual y minus predicted y, that means the actual value is bigger than the predicted value, which means we would predict that our estimate is actually going to be underneath the actual value. So we would expect our prediction to be too low because we would expect this to have a positive residual. So on your calculator, I tried to walk through all of that with that with that example. Basically, for any curved relationship, you can create a list 3 and a list 4. That is the logarithm of list 1 and list 2. And you can plot list 4 versus list 1, and you can plot list 4 versus list 3 and see if either of those are linear. You can then run a linear regression on the combination that appears linear using your calculator. You can then make the residual plot as well. So, you know, there's a lot of stuff your calculator can do here, and then you can see that's how I got that answer of 1032. Word of warning, if you're on your calculator, it might be tempting when you see this option to go with, oh my gosh, there's something down here that says exponential regression and power regression. Those must be awesome. They must help a lot. Well, they're not. Basically, in a future statistics class, you might learn how to use those. For this class, we are not going to use these. You'll notice you end up getting some different values. It is a different way to fit a model to a set of data, but it's not one we're going to use in this class. So just stick with transforming your data to make it linear instead, and then use linear regression. So here's a summary then. Here's a new method to check a power model. So we have 3 ways to check to see if something's a power model. One way for exponential model. I like using logarithms. So I would recommend, you know, just checking to see if that's linear, or check to see if that's linear, and then you'll know whether it's a power model or an exponential model. So, congratulations, you made it. That's it. You have now learned everything there is to know about AP statistics. I'm so proud of you. Well done. Bye now. Cody out. Make sure you hit that like and subscribe. Bye.